clients in the aerospace industry, Airbus, Bombardier, British Aerospace. And if my research does me right, it sounds like you might have some interesting opinions on machine learning and AI and engineering as well. So please welcome Dale Willey. Thank you very much.
All right, thank you very much. It's my great pleasure to be here, and thank you for the nice and high-pressure introduction. So I'll do my best. So I'm going to talk about a few things today. I'm going to give you an introduction to AeroTEC, what we do, and myself as well, a little brief history on myself. Then we're going to go on a bit of a journey, and we're going to talk about cycle time compression and technological innovation overall. There's obviously a lot happening in the world, and we'll talk about that briefly and how AeroTEC kind of frame our business and frame our approach through those lenses. And then we'll dive into some specific applications on simulation tools at AeroTEC, in particular Star CCM+, FeedMap, AimSim, and also how we use Teamcenter and NX overall through our design cycles. So we'll have some specifics on those tools and some very interesting applications that we're using them on some technologies that are really emerging in the aerospace sector right now and transforming the industry before our eyes. So that's the overall agenda. So AeroTEC is a company based here in Seattle, and our mission is to accelerate the evolution of aerospace. And we do that through leveraging all of our assets, whether that's our people, our tools, our processes, our facilities. We have a large flight test facility in Moses Lake, a few hours to the east. Very early conceptual studies, CFD analysis, wind tunnel models, requirements definition, system safety analysis, system architecture, detailed design, manufacturing, ground testing, flight testing, qualification, certification, the whole scope of product development. And outside of an OEM, it's actually fairly difficult to get, I think. So we're in a fairly unique position, and we get involved in a lot of very interesting projects. Before I talk a little bit more about the history of AeroTEC, briefly for myself, as you can probably tell by my accent, I'm not from around here. So I actually started my career in the UK, in the automotive industry, actually, with BMW. Then I worked for BAE Systems on the Eurofighter and Nimrod programs for a few years. I went backpacking around the world with my wife for 8 months. I have to tell you, the first day back at work after a trip like that is a very difficult day. So that was hard. Then I worked for Airbus on the A380, on the wing leading edge movable system, so mechanical systems. And then that transitioned onto the A350. In 2009, I moved to Canada and worked for Bombardier in Montreal. Started off in structures integration and then moved into flight test for a couple of years. We had a very interesting event where one of the engines exploded during a ground test. It's out there as a Transport Canada safety report if you'd like to review on that. And I ended up helping lead the team that repaired the wing. So in 161 days, with no structural repair manual, no facility set up to do a repair of that magnitude, we ended up getting the aircraft back into service. And Qantas had a 380, MSN number 32, I think, that had an engine failure in flight. So they had a structural repair manual. They had, procedures to repair that. And it took Airbus 169 days. So we beat Airbus in a flight test environment. So that's a nice little victory there, let's say. So it was in flight test, and then I came here to Seattle in 2015, started leading the engineering team, and then that morphed and evolved. And nowadays, I have oversight of all of the technical teams. So engineering, our test function, certification, we have a small software group, and also the program teams in order to bring kind of tight coupling between the program execution and the technical layers of the company. So that's a little bit about me. The company itself was founded in 2003, and it's really grown quite organically over its history. Started off as a bit of a spin-off from Aviation Partners Boeing and was doing a lot of winglet work, and in particular the testing of winglets. So all the winglets you'll see on 737s kind of came through AeroTEC. And then we did some work on the Catbird flying test bed for the F-35 program, where we put the nose on the front of the Boeing 737 and the wings as kind of canards on the side. And then got a real injection in 2014 with the Mitsubishi MRJ program. So we ended up leading most of the flight testing for Mitsubishi and developed our facility in Moses Lake. And also a lot of depth in terms of engineering and certification assistance to Mitsubishi. We have had some programs with Boeing, cargo conversions, More recently, we've done some work with Rolls-Royce on a next generation flying test bed, and a few other customers actually looking at that kind of concept as well, and we'll speak about that later. And then really a lot of the emerging startups coming out now. So magniX, we did some work with those guys and still are active on programs with them, and we'll talk to those programs later. Eviation, we have a program active right now with Universal Hydrogen that's very interesting, and we'll talk about that briefly. So a lot of really interesting emerging technologies coming through. So that's the company today. We have about 250 people spread across 4 sites here in Seattle, just north of here in Georgetown. Moses Lake, we have a manufacturing facility in Arlington to the north, and we just opened a small engineering office in Wichita, Kansas. Some quick numbers, we've done over 100 projects. We have about 250 people, as I mentioned, 4 locations, 182,000 square feet of hangar space. We did the largest pure battery electric powered flight demonstration on a Cessna Caravan a couple of years ago in the height of the pandemic. So that was challenging, but we basically stripped out the interior of a Cessna Caravan and installed batteries and installed the magniX motor and did all the integration of all of that. We have around 25 DERs on our roster or through our network. We do have AS9100 capability in manufacturing up at Arlington, and we have a very reactive experimental flight test manufacturing facility right next to the hangars in Moses Lake. So we can rapidly iterate and make parts and get them on the aircraft the next day to save time and cost and schedule in flight test. Very broad customer base. We touch everything from your regular OEMs through a lot of the startup community these days, tier 1 suppliers of components, again, whether that's electric motors or avionics equipment, modifiers and STC holders, and actually operators as well. So a very broad spectrum of people. And we leverage, again, all of our tools to help these people basically bring their product to market. So think of us as that kind of integration glue in the middle, understanding you have this product, you want to put it on an airframe, this is how we go about it, and then helping them through that journey. A couple of highlights in terms of the project. So here's that magniX Cessna Caravan that I mentioned. So again, interior was removed, and then all of the controllers and motors and all the thermal management, electrical load management, test, hazard assessment worked through, and then we did a few demonstration flights with magniX. Basically, the mission was a complete success. We got all of the data that they wanted, and now they've baked that into their next generation of motors that they continue to develop. And you'll see some of those working their way into products that will be certified over the coming years. So big success story with magniX. Another partnership with magniX that was recently announced in the press is a program with NASA. So NASA have awarded, I think it's north of $70 million to magniX in order to create an electric powertrain flight demonstrator. So this is a Dash 7 aircraft. Ignore the location of the motors on it. It's not going to look like this, but we're basically taking off 2 of the existing engines and replacing them with electrically driven motors. And so working with NASA and magniX to scope all of that out now and get into producing an asset that will really be beneficial for the whole industry, and the data that will be collected will feed into some of these emerging technologies that are coming through. So that's a big program for us that we're just getting started on. Universal Hydrogen. So here we're taking a Dash 8 aircraft, we're putting a hydrogen gas tank in the back of the aircraft. We're taking that gas and we're feeding it through one of the nacelles, which will have fuel cells, hydrogen fuel cells inside the nacelle. That hydrogen gas, as it goes through that fuel cell, then gets converted into electrons, which power, again, a magniX motor, which will then turn the prop. So we are right in the midst right now of releasing the final parts for that modification. It's starting to come together in Moses Lake. We will be modifying that aircraft very, very shortly, and later this year, you'll see that aircraft flying again as a demonstration. It's not going to be STC'd, but it's going to be a real demonstration to the industry, you know, of what's possible with hydrogen. Universal Hydrogen will get a ton of learning out of that program, and honestly, it's been a learning journey for all of us. You know, packaging up these complex emerging technologies that might not necessarily be in the final configuration, understanding all the segregation, how we're going to detect and monitor and vent hydrogen if it were to escape, you know, hazards and critical failure modes. So lots and lots of interesting discussions around the packaging and integration of a system like this. So very interesting. Another recent announcement is a program with Surf Air. So Surf Air are a very innovative, ambitious charter kind of airline operator out of California. And they are seeing an opportunity in front of them to help accelerate the electrification of certainly this class of aircraft, Part 23, Cessna Caravan. It's ripe for it. And so we're looking at hybrid electric configurations here. I can't go into too many details about what we're studying, but it will be some sort of hybrid electric configuration. And this will be an ST seed program. So this is another interesting one that's just about to kick off for us. Just to give you a quick flavor of all of the types of things we did on the Magni-X program, so you can see the kind of typical product development life cycle here, from when you launch the project and you scope out all of the requirements and you think about cert plan and your V&V plan, etc., all the way into actually going into any simulation and lab testing and rig testing, any structural analysis, getting into your detailed design, releasing those designs, manufacturing the parts, actually modifying the aircraft, and then going out and doing your validation testing and collecting cert data where appropriate. We didn't have to on this program because it wasn't ever going to be certified. It was a demonstrator program. But there's an example of all the types of things that AeroTEC got involved with on that program. Okay, so I said we're going to take a slight deviation here just to share some of the ways that we think about the disruptions and the evolution of technology, certainly from a simulation and computing perspective. I'm sure many of you are engineers in the room, so sometimes I can go off on a tangent. You got it? Tough crowd, come on. So from a cycle time compression perspective, what we're seeing, I think we can all feel this even as consumers, is that mass customization and endless configurations are the new normal. Think about the last time you bought a bike, a mountain bike or a road bike or a car or a TV. It seems like the options are becoming more and more endless. And there's probably a few things that are really driving that, including smartphone apps and scanners, so you can literally scan your living room or scan your body or your house or whatever, and it'll overlay things on top of it. 3D printing, giving you the ability to iterate and prototype very, very quickly, or even in some cases make production standard parts. Networked production systems that are kind of semi-intelligent. The transmission of high-speed data. Endless use case imagining, so lots and lots of people being very creative and coming up with where are the corners of the market that aren't yet addressed, and can I tailor a specific product for those corners of those markets. Flexible manufacturing systems able to retool and iterate very quickly so that we can get different production lines going almost instantly. And honestly, consumer and customer expectations are kind of increasing as well, because this kind of compounding flywheel effect from all of these emerging trends are working in unison. And then, of course, on the top of all of that, we have the digital tools that are really helping us to compress the cycle time overall. And again, that's creating this flywheel so that we can iterate and tailor products much more quickly. And then, of course, if it's faster, it tends to be cheaper, which means we can make more things, which gives more options. And, again, just a big flywheel. So what does that look like practically? So here's an example, the Humvee vehicle, probably produced to a spec by somebody, probably in the Pentagon at some point, looking at 80% of use cases maybe. But there's a lot of tailoring that could be done. Well, I don't want it to have this range. I'd rather strip out some of the mass of the vehicle. I'm not in a battle zone, or I want some jet jamming devices, or I want to carry more cargo. And so you see lots and lots of configuration modifications trickling in, and we're seeing this ourselves in aerospace as well. So Bombardier have just announced their defense division based in Wichita, for example. And so they're already looking very closely, and there are already assets out there on the Challenger product line, for example. So whether it's reconnaissance or cargo versions or all sorts of other applications, including kind of strike and tactical efforts as well. So we're seeing more and more extra options creeping into the product mix, if you like. So definitely a very real trend, and we're seeing that at AeroTEC as well. One other interesting graphic I have here is that the next decade is going to be very, very interesting. If you look at this graph, this is basically a plot of market capitalization over the last kind of couple of decades. And we are on the cusp of what's predicted to be a 3x market cap increase compared to the internet. Whatever the internet generated in market cap is about to be eclipsed 3x because of the convergence of 5 key technologies: the blockchain, genome sequencing, robotics, energy storage, and artificial intelligence. And certainly we're seeing that in energy storage, and what we're talking about with universal hydrogen and Magni-X and the battery energy density. And we're seeing the tools getting smarter and smarter, whether it's machine learning and AI. So it's definitely a very real trend, and it's going to see the continued acceleration and proliferation of some of these products. On the AI and machine learning side, again, some quick useful stats, but all you need to take away from these charts is that the cost to train an AI is plummeting at a very rapid rate. You look at some of the tools like GPT-3 and linguistic recognition or picture recognition. I think it's DALL-E is this new tool where you can type in, show me a picture of X plus Y plus Z, and it'll automatically generate a morphed image of some of these things. These tools are getting very, very powerful very, very quickly, and because it's on an exponential scale, it's going to disrupt things probably much sooner than many of us think. And the last thing to mention here, and we'll get back on track. I told you I'd take a bit of a deviation, but there's a really interesting article I read the other week from one of the former founders of Wired magazine, and he was eulogizing about this whole concept of the mirror world. So what does that mean? Well, the first technology platform, we basically digitized information, right? We created the internet, the World Wide Web. It subjected knowledge to the power of algorithms, and it became dominated by Google. The second technology platform digitized people or behaviors and subjected human behavior and relationships to the power of algorithms, and that was dominated by Facebook. And now we're on the cusp of the third technology platform, and this will digitize the rest of the world. So all things and places will be subjected to the power of algorithms and be machine readable. And whoever dominates will become the wealthiest and most powerful companies in history. So this is the kind of cusp and verge of what we're on. And again, as we talk about digital twins and digital thread and everything, the power of these simulation tools that we're talking about, we are kind of creating this reality as we go forward here. So I think the next couple of decades are going to be really, really interesting. Okay. Tangent finished. Let's get back on track. So simulation tools at AeroTEC. Before we talk about that, I'd like to just explain a little bit around how we think about how we layer the technology at our company. And again, AeroTEC's a fairly small company, but we basically have some working level tools. So on the left here, we have a kind of design suite. So we have, and we use both NX and CATIA. Don't throw rocks. We do use CATIA sometimes. So we have those kind of CAD systems. We have JAMA and DOORS as requirements databases. And then of course we have Teamcenter over the top of that, and then the whole accelerator suite, kind of encapsulating that whole design and configuration management perspective of the process. So we've got the design tools. We also have a couple of tools that handle our manufacturing and our maintenance. There's a little picture of a moped there because one of the tools we use we called Moped. And then we also develop our own in-house tools at AeroTEC. So we've got some specific software that we've created, whether it's to manage our test programs and define our test points and how we manage those test points, or limitations and restrictions on the aircraft, how we handle data, how we handle instrumentation. We've developed our own in-house bespoke tools. And then over the top of that, potentially we could use, the Mendix platform from Siemens to develop low-code apps to integrate some of our own tools with some of our other business level tools, for example. So we have NetSuite is our ERP system. We have some timesheet tracking and hours recording tools. We have some scheduling tools. So we have this kind of business level over the top of that. And then we have the network level above that. So we're talking, is it on-premise hardware or is it cloud-based infrastructure? So we kind of look at things on these three strata and how we can integrate and tie these a little bit more closely together. It's fair to say we're still at the beginning of this journey, but we are starting to see the benefit and the power of integrating these properly, keeping everything within the ecosystem, stop the manual transfer and copying and pasting of data, which gives us kind of real-time, accurate information. So we're really starting down this journey and looking at it very much holistically. And we're also seeing the trend from industry, right? Everything's going MBSE, model-based systems engineering, tying requirements to model, to NC program, to manufactured part, to inspection, or cert by analysis, taking credit for the really good high fidelity simulation work that we can do now. So again, it's leading us and driving us more and more into this direction to keep it all digitized, stop the manual transfer, and leverage the power of that, basically. Okay, so some specific applications. So one of the things I'm going to talk about here is a stub wing development. So by that, I mean a small wing that we would potentially put on the top of a large aircraft, say a 747. And there are multiple applications and customers that we've talked to about this and have actually done some work for. One other quick caveat as well, I'm not actually a super user or even a user of any of these tools. So if you have questions at the end, this table is where all the big brains are. I'm just explaining to you how we kind of go ahead and approach these things. So, so stub wing development. So, number one, we're trying to optimize the placement and the sizing and the profile of the stub wing for multiple, parameters and variables, right? So, what's the thickness over chord ratio as we go through the wing? What does that result in terms of drag and lift and stall characteristics? Is there any impingement on the empennage? Where's the engine placement optimized for? What does that look like from an inlet distortion perspective? So a number of very top level design goals, and we leveraged FEMAP and star CCM to make sure that not only was the positioning and profiling of the stub wing correct, but also the kind of structural integrity and the dynamic sort of response of the wing as well. So those are the top level overarching objectives. Here, a little bit of an eye chart, but you can see that on the left we have, the use of FEMAP and SimCenter to really help us hone in on the structural design. So as we develop the finite element model, making sure that we then evaluate all the possible side test station, we called it, general locations. So, is it too far forward, too far aft, what's the angle? Making sure that we've looked at all the different variations within that, and then kind of conceptualizing, mocking out the overall structural layout and attachment and how we drive those loads back into the rest of the fuselage. So that gives us basically a conceptual way of how we're going to mount the structure. Of course, in between all of that are our requirements. What does the statement of work say? What's the aircraft level requirements, the system level, any regulatory requirements? And then we go into the star CCM world. So developing our CFD models, looking at all of the aero loads, developing external and internal loads eventually, looking at what the OML shape looks like, and then what's the sensitivity of that from an aerodynamic perspective? Again, does it impinge on the empennage? What do we look like from an inlet distortion perspective? So you can see all those outputs coming down the right-hand side, coefficient of lift, coefficient of drag, what's the handling characteristics, stability and handling, stall characteristics, any structural impacts, sonic fatigue, thermal, Mach buffet, and there were some sensitivities on one of the programs we looked at with Mach buffet, for example, and just really optimizing it into that sweet spot. And there's obviously a number of parameters to play with. So that's kind of how we applied the tools. In more specific cases here, so these are baseline cases that we use because we're making very fundamental design decisions that would be extremely difficult to unwind later in the program. It's too late once we've modified the aircraft and spent millions of dollars to realize, oops, we have it in the wrong position. So we run a number of cases where we cross-check against baseline data. So here you can see on the top left image, it's CFD benchmark case for transonic flows. The bottom image is exhaust, I believe. Yeah, exhaust high-speed mixing flows. Then the image on the right was the kind of geometry for that transonic flow data. So it's really about cross-referencing what we're doing to some benchmark cases first before we get into the specifics, just to make sure that the output looks reasonable, looks good, so the model has some good foundation. So we always do that because we recognize that the importance of that and the very costly mistake of not focusing on that. Then we spent a lot of time actually going and validating actual aircraft from a loads perspective. So these are section cuts through the wing of a 747, and we instrumented it with pressure belts. And these are all the sensors of the pressure, the locations of the pressure ports. So we went and flew some, we called it baseline testing, some generic maneuvers under certain conditions, and then used that to correlate against our FEM prediction. So here's the section cuts of where the pressure ports were, And then here's a graph showing how that actually correlated to the prediction. So the gray line and gray dots here is the flight test results on the upper portion of the wing, I believe, and the yellow is the lower portion. And so you can see the orange is the CFD predictions, and it lines up very, very nicely with the actual results from flight tests. Some small deviations in some areas between the blue CFD prediction and the gray flight test, but again, just looking for that reasonable level of correlation, or can we understand and argue away some discrepancies and differences, or do we not need to worry about it? So we did a lot of work validating the CFD and also validating the kind of loads predictions and models that we had on that program. From a systems perspective, so we've got some examples here where we were looking at the cooling system. So this again was a flying testbed program where we have a test engine. We're taking a lot of energy from that engine, electrical and hydraulic, and we're dumping that into some system simulators, we called them. And so we need to make sure, because of that energy dump, we're building up a lot of heat. And so we need a very efficient cooling system, particularly in light of the fact that there were some very, very stringent requirements against this product. So it had to run in very, very hot outside air temperature conditions for long periods of time at high levels of thrust, because it's an engine development program. So started off with some very basic modeling, kind of block modeling on the left-hand side here, just to look at the overall architecture, put in some very crude parameters and see what we were looking like. And then as we refined our data and got more higher fidelity projections and went through kind of several loops of iterations, obviously the logic and everything else starts to spill out into a more detailed system schematic. And we were modeling all of this in AimSim and getting good correlation again with where we were projecting to go. So that's how we used AimSim there. We also used it for some modeling of hydraulic system response, looking at we have some engine-driven pumps off of the engine, so looking at what does the response of that system look like, and then using that to help us size things like tubing, reservoirs, accumulators, and again, got pretty cute, pretty smart around how we used AimSim to model some of that out with good effect. Different program here, just looking at baseline cases for cooling, powertrain cooling in particular, around the nacelle and the inlet. So we did some work modeling that out, and for the reason of here, what you're seeing is a side view of one of the nacelles. We had to put some kind of blisters on the external OML of the nacelle here in order to house a radiator. So air comes in through these blisters, is cooling down the radiator, which is cooling fluid from the powertrain system and then recirculating it. So it's all about making sure that we have the right thermal effects, that we're getting the right airflow through there so that we can balance the system correctly. And again, using those tools to help us simulate that out. Some work on CFD here. So I just want to talk about our overall resources, our hardware, first of all. So we have some internal compute power. So we have a couple of 3 or 4 machines actually with 256 core AMD based architectures. We typically use those for our smaller jobs that aren't quite as time sensitive, and we kind of balance that against maybe some external resources, cloud-based systems. We use Rescale, and we heard the previous speaker talking around that as well. So we use those for larger jobs or batching things up, and they're pretty good value for the large cases or very time-sensitive projects where we can get a lot of throughput very, very quickly. So we have a nice balance. We'll decide, can the schedule support just doing it internally and using our own assets, or do we need to go outside to the cloud and leverage that compute power? Resource is often a bottleneck for us, so we've kind of built some custom machines as well with large memory capability and high-end graphics, and our machines have a lot of RAM, as you can imagine, with NVIDIA graphics cards, etc. So done quite a nice job of trying to keep some good capability in-house as well as leverage the external resources. So those are our hardware kind of approaches. Here's some other examples. Again, stub wing. So now we're looking fore and aft, so you can see the wing and the kind of semicircle shape at the end there is the engine. And here we're looking at the combined structural and thermal effects. So how are we radiating heat how is heat being convected through this whole area, both externally and internally, and seeing what that means to the system and the structure as a result. Here's a view looking up at the underside of the aircraft. So this is the belly fairing. And so there's some louvers here. And this is where I was talking earlier about the system simulators. We're taking that energy from the engine, dumping it into some simulators in the belly fairing, and then having to vent some of that heat outside through these louvers. And so there's a lot of complex analysis here with star CCM, looking at how all of the air is flowing, what temperature gradients and buildups we're getting. And then actually, what does that mean even for the external environment? So here's a kind of isometric view, looking at how that hot air could be coming out for hours and hours of testing under very hot conditions. And then are we actually, running close to the limits of the tires or even the tarmac that the aircraft is sat on? And actually we were right at the limit. So we had to design some kind of deflecting skirts and that to get the hot air away from critical components really. So very, very stringent conditions, and we used star CCM to great effect to model out the whole airflow. We had a very complex system internally with even water spray systems and moving doors to kind of divert air into the right locations as temperature was building up. So it was a very, very complex system and complex analysis. Some images here now looking down on top of the aircraft in terms of inlet distortion. So again, using star and kind of dividing up the segments of the inlet and looking at what was the kind of max angle of inlet distortion that we could potentially handle, and in both directions, right, coming from kind of outboard the engine, but also coming from inboard and up and over the fuselage, and what does the whole airflow look like there. So again, some really good analysis and some great results that came out of that. Going back to thermal again, here's a little cutaway of the stub wing that we talked about. We have some ducting going through the structure there. And so we had to build up and look at, both using FEMAP and star CCM, what does that look like from a kind of radiated heat convection through the airspace? Are we going to build up heat into other rib bays? And also very specifically on any structure very, very close to the heat source itself. So what does the skin panel look like? What material does the skin panel need to be? How quickly does the heat build up? So lots and lots of detailed analysis in this area. And then, intelligent placing of holes or different material selections in order to cope with the thermal situation that we had. Again, some further details on this, mounting some bleed air lines to ribs, and again, looking at the local impingement of heat onto the ribs and making design decisions based off of that. We had some fuselage penetrations where some of the ducting was coming out with hot air. So again, how does that radiate through the skin? Do we need any knockdowns, or do we need any reinforcings or anything like that to cope with those localized effects? And in some cases, we actually installed some kind of thermal insulation and modeled that up to test to see what it looked like from a simulation perspective, and then went and tested it to see the effectiveness of those insulators, and again got pretty good correlation. So an interesting exercise. From a structural modeling perspective, so flutter is something else that we look at, and this is not the testbed program, but we had another program where we were looking at flutter on a new winglet installation. The results provided good indication in terms of speed and altitude and fuel state where the flutter modes were likely to happen on the outboard wing. And then we also simulated control surface failure scenarios, making sure that the actuation stiffness that would be needed would be present, again, in order to avoid flutter. This was an ITAR program, so can't tell you who it was, but it was a really good use, again, of SimCenter and NASTRAN to go through that flutter analysis. Here's one I can show you. So here's a 747 flutter. So the image in the upper right, I think, is just Boeing data off of the internet. And then in the lower left, this is our flutter model that we created. You can kind of see fairly good correlation with the wind tunnel model there, the way the wings and the fuselage are twisting and having fun. So lots of work going into the flutter models. FEMAP specific use cases. So on the 747, we had to build our own FEM on the whole fuselage, we were basically chopping a very large hole in the top of a 747 and then sticking a wing onto that. And so, how do you take all of that load? How do you shear it back through all of the structure? What kind of framework are you going to put in there? What's the reinforcing on the skins? What does that look like? We had some door surround structure in there, the floor beams. It was a very complex interaction of load, so we had to model up the whole fuselage, essentially, reverse engineer it, scan the OML, scan the IML, model everything out, and develop our own finite element model around that. And similarly, around nacelles, we've done a lot of work with VMAP as well to model, all of the load paths and generate our load models from that. Some other quick examples here on other programs. Again, creating FEMs around ailerons and landing gear, and then applying kinematics to that, and kind of keeping that digital ecosystem going, and then converting that into detailed design. So lots of work around using VMAP for that. Some other specific use cases here. So SimCenter 3D. We're looking at bulging on the top of the fuselage. Again, we're back to the 747 here. So right up on the upper deck, between frames. What does it look like due to pressurization effects? Are we getting any skin bulging? How much would that likely to be? Especially because we're modifying frames, we're chopping them or installing new frames. We need to understand the local interactions there. And then the lower image is skin buckling analysis. Looking at not just bulging, but the pillowing and buckling effects of the skin throughout the whole structure. So again, using SimCenter to help us do that. Okay, last section here really is around design and Teamcenter and the methodologies that we use as a company. So we are fairly agnostic in terms of CAD system. As I mentioned earlier, we do use CATIA, but we use a lot of NX as well. And we have the theorem translator in order to allow us to take both CAD systems and then display them simultaneously in a DMU. And it actually works really quite well. It's important that we keep Teamcenter at the right version in order to keep track of all the latest functionalities and versions with both theorem and other pieces of software. But it's been really good to work very collaboratively, not just internally, but also with customers as well. We get a lot of customers using different CAD systems, and so we can bring everything into the digital environment. So that's been good. NX, we use it obviously for a lot of our system modeling, whether it's wiring, tube routing, installation. We do it for high level, high precision surfacing. So whether we're doing an OML of the airframe or other surfacing work, we use NX there. We use a lot of the manufacturing tool sets. We have NX CAM, and we use it across 3 of our facilities, do a lot of the programming ourselves. And also, we're slowly kind of inching down the model-based definition pathway. So can we leverage the 3D model as much as possible? Can we detail out or annotate the part smartly? Does our supply chain have the capability to consume 3D models rather than drawings? And can we just keep that component of the design cycle to a minimum? Done a lot of work around standardizing our templates. If we have to go to a drawing, can we just use a minimally dimension drawing and also leverage the 3D model in the background? Or sometimes we have to go full 2D because the part requires it. There's a lot of key characteristics that really need to be seen on a drawing, so the supplier or whatever can check them. And again, putting the effort into defining those templates, getting the annotations and the notes standardized, and then just picking and choosing from the bench and optimizing the detailing part of the process that way. Product structure. So the way we kind of indent the product tree has become quite a hot topic for us, and the downstream consumers of all of our product structure and the IPL, the indentured parts list, making sure that the build up from detailed parts to sub-assemblies to next higher assembly, kind of top level assembly, is done in a thoughtful, logical manner, and then working very closely with the manufacturing engineers. How are you actually going to build this product, and are we structuring the tree in a way that it makes sense to everybody and they can consume that data? So we've spent quite a bit of time making sure that we're nailing down that process. We're still learning as we go through it and making sure all the stakeholders are a part of it, but we are spending quite a bit of time doing that in Teamcenter. and then making sure that we can extract an IPL from that for downstream consumption by other parties. And again, very much recognizing that there are some great inbuilt tools within the Siemens suite these days that we can and should be using. We're a little bit too manual still at the moment, and as a result of that, there's some duplication and sometimes some error. So we're trying to move ourselves, more into the direction of how do we keep the data digitally native and not have to export to an Excel that somebody then uses, and then it becomes out of date, and then we have to go back and cross-check everything. So trying to keep the data very native in the system. This one was just talking about how we actually go through that, and then the BOM structure that we get out at the end of that, so we can fairly quickly skip over it. Another big thing that we've come to realize is the importance of attributes and making sure that all of the attributes are filled out in a very standardized way. Again, we have downstream customers, whether it's supply chain, placing a PO, or the manufacturing engineers, or people actually doing the work on the shop floor. So again, being very thoughtful around exactly how are we describing the part, is the material type in there and written in such a way that it's clear exactly what we need. Even is this a bio-furnished equipment component? Is it a component off the shelf? Is it a piece of hardware? Having these categories so that people can filter for the type of part that they're looking for. So we're spending quite a bit of time thinking about how we define attributes and how that data is used downstream. And then lastly, really talking about workflow. So, we obviously design our workflow based on how we think we're going to go about releasing parts for a program. And then sometimes being adaptive enough to recognize that we might need to change the workflow. So example here is designer has a part that's ready to be submitted for release. So he or she launches it into the workflow. We have a data control group, so they take it, they'll do some quick checks. Does everything look good? Are the attributes in there? Okay, looks good, let's launch it into the checking and release cycle. So we get checkers assigned, whether that's a design checker, the stress sign off, and then we go out to the manufacturing check. And that's an area where we've seen actually sometimes we need to pull those guys in a bit earlier because we were then breaking the chain. If manufacturing engineering rejected it, sometimes it went all the way back to the beginning of the workflow. So having these adaptive workflows where we can say, actually, that doesn't make sense, let's tweak it, has proven to be beneficial for us. And then it goes for kind of final sign off and then gets released by data control. Somebody can create a PR, a PO, and then off we go. And then even thinking about, stop work orders, there's something wrong with the part, I can't actually manufacture it. And so how do we control that workflow inside the system as well? So we've done quite a bit of thinking about the overall workflow of design, release, and then downstream impacts. Okay, that is basically it. Thank you for your attention. Are there any questions? And if there are, we'll deflect them over here.